Hello. Previously we have covered the natural response of second-order circuits due to the initial energy stored in the capacitors and inductors. Now we will cover the forced response of these circuits, and by adding the natural response and forced response, we will have the complete response of these circuits. Specifically, we will find the forced response of a parallel RLC branch for a current input. Then, by adding the natural response and forced response, we will find the complete response of the circuit. And at the end, we will briefly look at the different root configurations in the complex plane and what type of circuit responses these cause. Let's remember the natural response of second-order circuits. In the overdamped response, we have two real roots, and the response is in the form of A1 times e to the S1t plus A2 times e to the S2t. In the critically damped response, these roots are overlapping, and we have a response in the form of A1 plus A2 times t times e to the minus alpha t. And as a third response, we have complex conjugate pair of roots, and the response is A1 times cosine omega d times t plus A2 times sine omega d times t multiplied by an exponential decay in the form of e to the minus alpha t. The differential equation for a second-order circuit is given by this equation. Second derivative of x with respect to t plus a1 times dx over dt plus a0 times x is equal to some type of forcing function f of t. And the forcing response x of s must satisfy the same differential equation. Right now you might wonder why we can solve this equation only for the forcing input and get the forcing response. This is actually one of the results of the superposition principle. We are considering all of these as separate inputs and finding the response of the system for each of those inputs, either due to the initial conditions or due to the forcing functions, and we are adding all of them together to find the complete response of the system. We need to find xf such that the summation of xf and its first and second derivatives here satisfy the equation too. In most cases, xf will be a function similar to the forcing function f of t, such that the above conditions hold true. So in other words, if we have an input in the form of a sinusoidal, then the output will be another sinusoidal of the same frequency with a different amplitude and phase. We can just generalize this to other types of inputs as well. Let's see how we do this. For instance, the forcing function is a constant. The assumed response is a constant as well. Our forcing function is in the form of k times t. The assumed response is in the form of at plus b. We would also have the same type of assumed response if the input would be kt plus another constant such as x. Kt squared, the response will be at squared plus bt plus c. For k times sine omega t, the assumed response will be a times sine omega t plus b times cosine omega t. Or we could have written it in the form of c times sine omega t plus phi. And if the forcing function is in the same form of an exponential decay, k times e to the minus at, the assumed response will be also a times e to the minus at. So basically, these constants a in the exponent are the same. Similarly, here the frequency of the input omega and the frequency of the output are the same as well. Alright, we need to find the response for the inductor current IF. For the input, IS is equal to 8 times e to the minus 2t after t greater than 0. R is equal to 6 ohms, L is equal to 7 henries, and C is equal to 1 over 2, 42 farads. Let's try to write the KCL for this top node. V over R plus I plus C dV over dt is equal to IS. For t greater than or equal to 0. And in addition to this, I know that v is equal to L di over dt. And accordingly, I can write L c d second derivative of I over dt plus L over R times di over dt plus I is equal to is. And from here, I can propose a solution in the form of if is equal to b times e to the minus 2t. And dif over dt is equal to minus 2b times e to the minus 2t. The second derivative of if, dt squared, is equal to 4b times e to the minus 2t. And I can plug these into this equation and try to find the coefficients accordingly. Okay, now I have equation 1, which should satisfy the proposed forcing function and the input. And let us write it using the parameters for RLC. L times C is 1 over 6 times the second derivative of if over dt squared plus L is 7, R is 6, 7 over 6 dif over dt plus if is equal to, let's write it, 8 times e to the minus 2t. And here I can multiply everything with 6, both sides, left hand side and right hand side. dt squared plus 7 dif over dt plus 6 if is equal to 48 times e to the minus 2t. Of course, I just have expressions for if, dif over dt, and second derivative of if with respect to time here. So let's use those. 4b times e to the minus 2t plus minus 14b times e to the minus 2t plus 6 e to the minus 2t is equal to 48 times e to the minus 2t. I can write everything in the parentheses of e to the minus 2t. Accordingly, I will have minus 4b equal to 48, and from here I find b is equal to minus 12. Accordingly, the forcing function output of the system with respect to the time will be minus 12 times e to the minus 2t. Of course, this is not the complete response of the circuit. In order to have the complete response, we need to also calculate the natural response of the circuit due to the initial conditions, but right now we don't have those. Now I have an interesting input here. My input is a constant I0, and I have my equation here. Let's propose the solution if is equal to some type of constant, let's say d. dif over dt will be equal to 0. Similarly, the second derivative with respect to time of this output will be equal to 0 as well. Accordingly, I can write this equation here as 0 plus 0 plus if is equal to is, and accordingly I find if is equal to is, which is equal to I0. So it was easy to solve this circuit for this step input for the forced response. So basically, the output of the circuit for a step input is again a step with the same magnitude for this specific case. Let's cover an important special case for the forced response. Assume that a second order circuit has the differential equation of this form. Second derivative of I with respect to t plus 7 di over dt plus 6i is equal to 6 times input current S. And assume that Is, the input current, is 3 times e to the minus 60. And when I put the current here into the equation 1, I end up with this expression. Now, firstly, let us find the characteristic equation of this system simply as s squared plus 7s plus 6 is equal to 0. And if I were to factorize this, I end up with s plus 1 times s plus 6. And according to, I can write my poles as s1 is equal to minus 1, s2 is equal to minus 6. And obviously, the natural response of this circuit will be in the form of In is equal to a1 times e to the minus t plus a2 times minus 60. And since I told earlier for an exponential forcing input, the forcing response of the system will be in the same exponential form, you would naively use this type of assumed response. If is equal to b times e to the minus 60. But if I were to put this third equation into the second equation, I end up with this expression. If we disregard e to the minus 60, I end up with 36b minus 42b plus 6b is equal to 18. And this gives a solution in the form of 0 is equal to 18 times e to the minus 60. And this is an impossible solution. So I did something wrong. We need another form of the forced response when one of the natural response terms has the same form as the forcing response. Here we are doing the usual trick as we were doing in the natural response. We are multiplying our proposed solution with t. So if becomes if is equal to b times t times e to the minus 60. And we will plug in this term and its derivative to this equation. Let's try to take the derivatives. It will be messy. So it will be minus 6bt times e to the minus 6t plus b times e to the minus 6t. And the second derivative will be simply minus 6b times e to the minus 6t plus 36b times t e to the minus 6t minus 6b e to the minus 6t. So can I simplify these terms? I don't see an easy way of simplification. I can write it as minus 12b times e to the minus 6t plus 36b times bt times e to the minus 6t. Now let's plug these into this equation. All right, let's plug in this, and this into this equation. And for the sake of simplicity, I will write everything in the parentheses of e to the minus 6t. So I will have minus 12b plus 36 bt, and then minus 42 bt plus 7b plus 6 bt is equal to 18 times e to the minus 6t. And this forcing response should just work at all the different times. So at t is equal to 0, we have minus 12b plus 7b is equal to 18. And from here I calculate b as minus 18 over 5. If b is this, then my forcing response will become I of t is equal to minus 18 over 5 t times e to the minus 6t, and I find my forced response of the circuit this way for this special case. We can formalize what we have done. In general, if the forcing function is of the same form as one of the components of the natural response x subscript n1, we use xf is equal to t to the power of p times xn1, where p denotes the lowest power of t, which is not used in the natural response. And this way we can propose new forced responses for the circuit. Let's learn the complete response of an RLC circuit. The complete response is the sum of the natural response and the forced responses. In other words, x is equal to xn plus xf. Assume that we have an RLC circuit with the following differential equation and with this set of parameters. And if we plug in these parameters, we end up with the differential equation shown here. Second derivative of v with respect to t plus 5 dv over dt plus 6v is equal to 6 times vs. And we will first find the natural response. And for that, I use the differential operator and write this left side as s squared plus 5s plus 6. And by solving this quadratic equation, I end up with s1 is equal to minus 2 and s2 is equal to minus 3. Accordingly, I can write the natural response as Vn is equal to a1 times e to the minus 2t plus a2 times e to the minus 3t. But this is only one part of the solution, and I also don't know the coefficients a1 and a2, for which I will use the initial conditions to find them. The natural response of the circuit is Vn is equal to a1 times e to the minus 2t plus a2 times e to the minus 3t. And the forcing function to the circuit is equal to 2 times e to the minus t divided by 3. As you can see, the exponents of the natural response is minus 2 and minus 3t, whereas the exponent of the input or forcing function is e to the minus t. So they are different. Therefore, we can easily propose Vf is equal to b times e to the minus t as the forced response. And we can find the coefficient b by substituting 1 into the general equation of my circuit. In order to do this, I will need to find the first derivative of the forcing function which we propose, which is equal to minus b times e to the minus t. And the second derivative of it will be accordingly b times e to the minus t. I love exponential functions. Their derivatives are in the same form. Now let's plug this in. Everything in the e to the minus t parentheses. It will be b plus minus 5b plus 6b is equal to 6 times 4 times e to the minus t. And from here I get 2b is equal to 4 and accordingly b is equal to 2. Now I can write the whole response of the circuit as the sum of the natural response plus the forced response, and that will be equal to a1 times e to the minus 2t plus a2 times e to the minus 3t plus 2 times e to the minus t. Now I still have one problem. I need to find a1 and a2, and for that I will use the initial conditions. Alright, I am given two initial conditions. V0 is equal to 10 volts and dV0 over dt is equal to minus 2 volts per second. So let's use this equation to evaluate V0, and this will be equal to A1 plus A2 plus 2 is equal to 10. And I can write this simply as A1 plus A2 is equal to 8. Now let's take the first derivative of this equation. dV over dt is equal to minus 2a1 times e to the minus 2t minus 3a2 times e to the minus 3t minus 2e to the minus t. And if I evaluate this at t is equal to 0, I end up with minus 2a1 minus 3a2 minus 2 is equal to minus 2. So accordingly, I have a1 plus a2 is equal to 8. And similarly, I have minus 2a1 minus 3a2 is equal to 0. Let's multiply this equation with 2. I have 2a1 plus 2a2 is equal to 16. Let's add these two equations. I end up with minus a2 is equal to 16. From here, I calculate a2 is equal to minus 16. And by using this equation, I calculate a1 is equal to 24. And therefore, I can write my complete response as a1 is 24. 24 times e to the minus 2t minus 16 times e to the minus 3t plus 2 times e to the minus t. So this way we concluded the solution of this problem and found the complete response of this circuit. Alright, we need to find the complete response Vt for t greater than 0, and we will assume that the circuit is at steady state at t is equal to 0 minus before the switch changes position. So I need to first find the initial conditions. For that, I will write the circuit, I will draw the circuit for t is less than or equal to 0. So in that case, we will have here our plus minus 10 volt source. Here I will have 4 ohms. This is 10 volts. The inductor obviously behave as a short circuit. And we will have here 6 ohms. And the capacitor will behave as open circuit. And here we will have plus minus V. If I were to define my reference node here I see that I have a voltage divider and here I have V, and accordingly V will be equal to 10 volts times 6 ohms divided by 10 ohms, and accordingly it is equal to 6 volts. So this will be my V0 is equal to 6 volts, one of my first initial conditions. The second one, the I is defined this way. So the I will be also flowing through this branch. So I will be simply equal to 10 volts divided by 10 ohms and is equal to 1 amperes. Therefore, I can also write I0 is equal to 1 amperes. So I found my both initial conditions for this circuit. After finding the initial conditions, let us draw the circuit for t greater than 0. Here we will have plus minus Vs, 4 ohms, 1 Henry, 6 ohms, and here plus minus 1 over 4 farad capacitor. And I can draw this like this. Here the voltage over the capacitor is defined as V, and if I were to define this as the reference node, I would also have V at this point, and the current I is defined this way. So accordingly, I can write that V is equal to L di dt, L is equal to 1, di over dt, plus 6 times I. And in addition to this, I can also write the KVL for the left loop, and I can write potentially, or KCL for V, V minus Vs over 4 plus I plus 1 over 4 times dV over dt, that is the current going this way, I capacitance, let's say, is equal to 0. Now I can use these two equations in order to write them using the S operator for d over dt and solve them algebraically. Now we will convert 1 and 2 using the differential operator d over dt to an algebraic form. That will be v minus si minus 6i is equal to 0. From here I can write I is equal to V over S plus 6. And the second one will be V1 plus S plus 4I is equal to Vs. If I put I into this equation, I end up with V1 plus S plus 4V over S plus 6 is Vs. From here I can write further in V parentheses 1 plus S times S plus 6 plus 4V is equal to Vs times S plus 6. And from here I can collect the term and write S squared plus 7S plus 10V is equal to Vs times S plus 6. This is my characteristic equation, and I can solve for the roots of it. S12 will be equal to minus 7 plus minus square root of 49 minus 40 divided by 2, and this will be accordingly, what will it be? 3. So minus 10. S1 is equal to minus 5, and S2 is equal to minus 7 minus 4 minus 2. So these will be our two roots of the characteristic equation. Let me convert 1 to the differential form again. Second derivative of v over dt squared plus dv 7dv over dt plus 10v will be equal to dvs over dt plus 6vs. And using these two poles, I can write the v natural as a1 times e to the minus 5t plus a2 times e to the minus 2t. And using the form of the input, I can write the forcing response as b times e to the minus 3t. This is good because we have here minus 5, minus 2, and minus 3, so they are not overlapping. So I will now try to solve my circuit for the forced response. Now the forced response should satisfy this equation. And in order to figure out that, let us take the derivatives of that. dvf over dt is equal to minus 3b times e to the 3t minus 3t. Second derivative of that is equal to 9 times b times e to the minus 3t. And let me do that also for dvs over dt. It is given here, so that will be equal to minus 18 times e to the minus 3t. And if I were to write everything in the e to the minus 3t parentheses, the left side will be 9b plus minus 21b plus 10b is equal to, so equal to dvs over minus 18 plus 36 times e to the minus 3t. So let's just do some algebra. I have minus 2b is equal to 18, and from here I find b is equal to minus 9. In other words, forced response of this circuit will be equal to minus 9 times e to the minus 3t. I found that. Now I need to find the natural response to have the complete response of the circuit. I have here the expression for Vn, and here I have the expression for Vf, and accordingly I can write V is equal to Vn plus Vf, which is equal to a1 times e to the minus 5t plus a2 times e to the minus 2t minus 9 times e to the minus 3t. And I have the initial condition for v0. Accordingly, at t is equal to 0, a1 plus a2 minus 9 will be equal to 6. And from here, I get my first equation. a1 plus a2 is equal to 15. I need to find another equation right now to solve for these two unknowns, a1 and a2. Now, how we will find the second equation? We will do this classical trick of taking the derivative of dv over dt, which will be equal to minus 5a1 times e to the minus 5t minus 2 a2 times e to the minus 2t minus plus 27 times e to the minus 3t. However, at dv0 over dt, this will be equal to minus 5a1 minus 2a2 plus 27. Where will I find the equation for dv0 over dt? Previously, we had found that v plus 4i plus dv over dt is equal to vs. And now we know all of these elements, and I can write that dv0 over dt is equal to minus v. At 0, I have minus 6, minus 4i minus 4, plus vs at t is equal to 0, which is 6, plus 6. And from here, I get dv0 over dt is equal to minus 4. So accordingly, I can write that this expression is equal to minus 4. And I can write this expression as minus 5a1 minus 2a2 is equal to minus 31. So this is one of my equations. This is the second equation. Now I will need to solve them. Alright, let me multiply this with 2. I end up with 2a1 plus 2a2 is equal to 30. Let us sum these two equations. I have minus 3a1 is equal to minus 1. From here, I calculate a1 is equal to 1 over 3. I can use this equation in order to calculate a2. 1 over 3 plus a2 is equal to 15. Accordingly, a2 is equal to 15 minus 1 over 3, which is 44 over 3. So now I have a1 and a3, and I can write the natural response of this circuit as 1 over 3 times e to the minus 5t plus 44 over 3 times e to the minus 2t minus 9 times e to the minus 3t, and this final expression concludes the solution of this problem. Let's recap the natural response of second-order circuits. For the overdamped case, I have S1 over S2 is equal to minus alpha plus minus square root of alpha squared minus omega 0 squared, two real roots which are different, and according to the natural responses in the form of a1 times e to the s1t plus a2 times e to the s2t. For the critically damped case, I have two overlapping real roots at minus alpha, and the response is a1 plus a2t times e to the minus alpha t. For the underdamped case, I have a complex response. The poles are S1 and 2 is equal to minus alpha plus minus j omega d. Here j is the square root of minus 1, the imaginary number. And therefore the response is an exponential decay e to the minus alpha t multiplied with an oscillation a1 times cosine omega d t plus a2 times sine omega d t. We can use the complex plane in order to understand the behavior of dynamical systems. Here in this plane, x-axis is the real and y-axis is the imaginary axis. And in the overdamped case, we have two real poles at these different locations, and then the response is here. For the same system, if it is critically damped, the roots are overlapping and the system is again in exponential decay without oscillations but faster than the first response. In the underdamped case, we have two complex conjugate poles and both of them have both real and imaginary components. The real components are the same. However, the imaginary components are conjugates of each other. That means they have the same magnitude but different signs. And according to the response is an exponential decay again. However, this exponential decay has oscillations inside and is following the general envelope of e to the minus alpha t, while we are also having oscillations in the behavior. The extreme case of the underdamped response is the undamped response, where the roots don't have any real components, and in this case we have oscillations which are sustained forever because the system does not dissipate any energy.